Welcome to this demo lecture. So actually, I have tried to make a separate lecture for holding just the proofs of the lecture 2. So basically, we'll be covering some of the proofs that will be useful in if you need case, as this will be the dot product and another one for the eigen and another one also for the symmetric matrices to show that why the eigenvectors are orthogonal and the eigenvalues are real. So basically, the first one is to prove why on Earth A dot B equals to length of A by length of B by the cosine of theta, where the first equation was just summing the element-wise multiplication between the vectors. Okay, so if we take a simple example here, these three vectors A, B, and C, and we have this angle between the A and B. From the cosine law, we remember that this C squared can be represented by A squared plus B squared minus 2 length of A, length of B, cosine the angle between them. Okay, so this is the cosine law, which is formulating this part. And if you know from the first, from the lecture, the original lecture, that C squared is just C dot C. Okay, so from the previous distance vector law is P. We are moving from this point to this point. This is the P, and since C, we are moving to this point. So the overall movement is just moving to A. So we can represent B plus C equals to A, and hence C can be equals to A minus B. Okay, so why do we need C here? To just replace it, this C squared by A minus B squared. And since this C dot C, so it will be A minus B dot A minus B. And therefore, if we do the mathematics, we'll be getting A squared B squared minus 2AB. And from equating these two equations, we get knocking off A square, and knocking off B square, and negative 2 by negative 2. So we get that A dot B will be equal to length of A, length of B, cosine theta. So this is how we can prove that A dot B is this formula. Moving forward to the eigenvalues calculations, we have here 3 different ways to calculate the eigenvalues, and they are pretty much a tricky ones, not hard, but just easy to solve this. So if you remember from the original lecture that x is the eigenvector and it will not change the direction, it will be the same direction, but it will be just scaled by a factor, or also can be a division, a factorization part. And here we are going to calculate it in 3 separate ways. One way is to calculate the trace and the determinant and putting these two values inside this trinomial equation. So what does the trace means of a matrix? The trace is sum of the diagonal. What does the determinant mean? The determinant can be equating this absolute value of the matrix, which is multiplying this diagonal by subtracting from it this diagonal, if this 2 by 2 matrix. So for example, if we can take this matrix here and calculate the trace, it will be 10, and the determinant, it will be 2 by 8, it will be 16, minus 7, it will be 9. So here we calculate the trace and determinant pretty easy, and we should just put them in this equation. So the trace will be on the negative sign, and the determinant will be in the positive sign. And here we have these lambda values from this trinomial equation. Also, another simple equation is to find the determinant of a minus lambda I and set it to 0. So what does subtracting this lambda I from A is just subtracting this lambda from the diagonal of the matrix A, and it will be pretty much this value. So the determinant will be multiplying this diagonal and subtracting this diagonal. So it will be finding after the mathematics formula will be the same output here, and the eigenvalues will be 9 and 1. Also, this last approach, which I found like pretty neat, is finding the mean of the diagonals. So if it is 2 and 8, 10 divided by 2 to find the mean. So the mean of 2 and 8 is 5. And the determinant of the A is also 9. So we can put them in that formula and find the two eigenvalues. So it will just be helpful for the 2 by 2 matrix. M mean of the diagonal, which is 5, plus or minus m squared minus b, and it will be showing the same output, 9 and 1. Okay, so moving to the last proof, which is actually two proofs. First, to show that eigenvectors of the symmetric matrices are orthogonal, and showing the eigenvalues are real. So let's start by the first one. If we have this ax equals to lambda x equation, which is the eigenvector equation, and ay by beta y, which y and x here are eigenvectors of the matrix A, and beta and lambda are eigenvalues. And we are here multiplying y transpose by the first equation and x transpose by the second equation. Okay. And after that, we are taking the transpose of this number one equation. So transposing vector matrix vector will be swapping their order. So instead of yax, it will be xay, and the transpose will be applied after the swapping. And the same for the second side, yx, it will be xy, and we will be swapping also the transpose. So it will be here x transpose ay and x transpose y. And y, there is no A transpose here because this matrix is a symmetric. So A and A transpose is pretty much the same, you know, from the properties of the symmetric matrix. The transpose is the same as the original. And if we subtracted these two equations, then we knock off the left-hand side, and we get this as the right-hand side, beta minus lambda and x transpose y. So we can cancel this scalar. So x transpose y is set to 0, which means the dot product is set to 0, which indicates that these two vectors are orthogonal. Okay, and the second proof is to prove the eigenvalues are real. So in that case, we'll be falling off the same. We'll start with the same equation and taking the conjugate of this equation. The conjugate is pretty much taking the if it was having imaginary numbers, we'll take the opposite sign of this imaginary number, the complex conjugate of it. Okay, and after that we'll be transposing it. So as you know, transposing is swapping the order. If it was a matrix vector here, it will be a vector matrix, and applying the transpose, and you know A transpose will be the same A because it's a symmetric matrix. And then we multiply 3 by x from the right, and you will see that x transpose A x will be x transpose x. Okay, and we multiply from the left x transpose. We multiply the first equation by x transpose, so you will get the same as the fourth equation. So here we can find from 4 and 5 that the lambda will be the same as the lambda transpose. Because if we have just knock off these two values, so the lambda will be equals to the lambda conjugate. So in that case, there is no complex values, and the conjugate is the same as the real value. At this point, we can end our appendix of the second lecture. See you soon, and goodbye.